So hi all, welcome to this lecture 6 of Unconstrained Optimization lecture series. The Today we are going to discuss convex sets. Convex sets are why are we discussing convex sets is because convex functions are a very important class of functions which are very useful in optimization theory. This is because optimization has convex functions have some special properties which make it easier to optimize them, and it is very easier to learn theory of optimization using convex functions. So before learning about convex functions, we like to know what are convex sets, and that is what we are going to study today. So before starting, let's just recall what we studied in the last lecture. So in the last lecture, we discussed some algorithms for the one-dimensional optimization. So the input was one for a function, and we optimized that. So we looked at some derivative-free methods like dichotomous search, um, Fibonacci search, and golden section search. These three we looked at. We saw that for dichotomous search, uh, and two re- two function evaluations were required per iteration, so that was the disadvantage. Then for Fibonacci search, only one function evaluation, so we solved that using Fibonacci search, in which only one function evaluation was required, but it had some other disadvantage that it required n the number of iteration steps beforehand. Before starting the iterations, we need to specify what are the number of steps. So that was a disadvantage, and to solve that, we use what is called golden section search, and it does not require n. So that is the thing, and then we also looked at some derivative based methods, um, mm, in which we looked at bisection method, which is just a variation of dichotomous search. So basically, if we have a closed set, we find a midpoint, find the derivative at that point, and if so, we find a midpoint, we find the derivative, and if it is positive, then we change the set to lower limit to that point, and if it is negative, then we set the new new interval to that point to the upper limit of that set. So that was the bisection. It's similar to dichotomous search. It's just that instead of calculating 2 points, we just calculate the derivative at that point. And then there was Newton method, which we didn't discuss in the last lecture, which we'll discuss today. So let's get started with Newton's method. So before getting started in Newton's method, let's just you might have learned about Newton's method in your undergraduate or any other courses. So it's a method that is used to find roots of a function. So it is used to find roots of a function. Let's say you have you have a function and you want to find root of it, approximate root, then we use Newton method. So let's look at an example that how we find. So let's say we have a function fx given by this. So this is a very simple example. Its root exists at plus and minus root 2, that we already know because it has an analytical solution. Let's try to solve it using Newton's method. So how will we do it? Uh, so let's say this is the graph of the function. Okay, so this is our root. So what we do is, let's say we find some initial guess, x naught. Let's call it x naught. We find a derivative at that point, and look where does it cut the x-axis, and then at that x1 we again find the function value. We again find a derivative and go on, and we converge to the root in that manner. So this is what Newton methods does generally to find the root of a function. Remember, we have to find we use this method to find the uh, uh, optimization of a optimal value of a function. So the next thing is how can we use this in optimization? So let's say this is a problem. So this is the standard problem we have been discussing, that minimization of x over r, fx, where fx is a single input real valued function, and it's twice differentiable. So it's twice differentiable. Then what should be like what is the how can we use Newton methods to optimize this problem? So what Newton method does is, so it's at any iteration k, it constructs a quadratic model model qx, let's call it qx, of function fx. Okay, so also we are constructing the model in such a way that it agrees with fx. It, by it I means qx. Qx agrees with fx up to two derivatives. What does that mean? That at xk, the derivative of fx, fx and double derivative of fx are equal to the derivative of qx and q double derivative of qx at xk. So I'll just write it. So which means that q dash xk equal to f dash xk and q double dash xk f double dash xk. So this is a based on this we can form a quadratic model. You can also look at it another perspective. You are basically approximating fx to qx by expanding its Taylor series and truncating the higher order terms. So okay, so let's say this is the approximate quadratic model qx at xk, around xk. This is the approximation of fx at around xk. Now we estimate xk plus 1 by minimizing qx. So what we do is we try to minimize qx here. So we approximated fx and now we will minimize qx. And through that we'll get xk plus 1. So what does minimizing means? We'll take the derivative. Xk plus 1 is where this gets minimized. So derivative of qx at xk plus 1 is 0. Which what does that give me? F dash xk plus f double dash xk. Sorry, it's half times. So this will become x minus xk. Okay. So this needs to be 0. So what does that tell us? X k plus 1 equals xk minus f dash xk f double dash xk. And what we'll do is we'll repeat this procedure. Xk at xk plus 1. So what we did was we assumed some point xk. We approximated our function fx to a quadratic model qx at that point, such that its first and second derivative match. Then we like minimize that quadratic model by derivating equating it to 0, through which we got this relation xk plus 1 is equal to xk minus f dash. So basically this is the update step of our algorithm. So what we do, we initialize xk, find f dash xk, f double dash xk, and next xk plus 1 is just this value that is given in the box. So through this step, we can like write an algorithm. So we initialize our initial point x naught, some tolerance level epsilon, and our iteration variable k is equal to 0. Then we write a stopping step. So if f dash x, that is the derivative of x, is greater than epsilon, uh, or this means that stop when the derivative becomes lesser than some tolerance level. That's what it means. So if is greater than epsilon, then update step is this. So you update the next point to be equal to this and update the iteration variable, and at the end give the output as xk. So this is a simple algorithm. This is a second order. It uses second order derivative. All the bisection uses only first order derivative. So Newton's method uses second order derivative, and it's quite faster compared to first order derivatives. It's fast, but it has its own disadvantage, which we'll look at now. So let us look up some remarks over this uh, remarks that, or what you call, some properties or some points to be noted about Newton's method. So if we start, if we start at any arbitrary points, then Newton methods need not converge at the stationary point. So it may not converge to the minimum points. Okay, so that is the case. Newton methods. Why? So that means a Newton method is faster, but it does not guarantee convergence. So that is one disadvantage that we have. So this is a disadvantage. Second thing is, so if you want it to converge, so if is sufficiently closer to stationary point, then Newton method converges. Okay, so it has to be sufficiently closer to the stationary point, only then it will converge. If it is far, it may diverge. So now let us look at some examples how to use Newton methods to solve them. So the first example is this. Let's say this is the function. We have to minimize uh, this polynomial function. Okay, so which is 1 by 4 x to the 4 minus uh, 5 by 3 x cube minus 6x square plus 19x minus 7. So, so this is what we have to solve. So let's assume fx equal to x to the power 4 by 4 minus 5x cube by 3 minus 6x square plus 19x minus 7. What is its first derivative? Let's assume it's gx. So it will be x cube minus 5x square minus 12x plus 19. Okay, now let's plot it out. So what uh, So this is gx. This plot is of gx. And these are the 2 points. Let's say these are the zeros of gx. So these are actually the minimas, or some stationary points of fx. So this is where we have to get. So the thing is, with Newton method, if we choose a initial point closer to, let's call these stationary points S0 and S1. Okay, so if we choose these points closer to S0, let's say X0 is closer to S0, then it will converge to S0. Okay, with Newton method, you can't find SN, S1. And if you change the initial condition and assume it nearer to S1, then what you will find is it will move slowly and slowly closer to S1. So it will converge to S1. So Newton method is highly sensitive to its initial condition. So if you have to find a stationary point of a system, then you have to choose the initial condition properly. And based on the initial condition, the Newton method may converge to different stationary points. Now look at one another example in which we'll see some disadvantages of the system of Newton's method. So this is, let's say this is one of the functions, and let's fx is equal to log e to the power x plus e to the power minus x. Okay, so this is the function. Let's its first derivative is equal to gxb, but it will be e to the power x. Sorry, power x. Sorry, it's not x plus e to the power minus x, then chain rule e to the power x minus e to the power minus x. So this will be the its derivative. Okay, a derivative of fx. Um, so let's draw its graph. Draw the graph of the derivative. So it will be something like this. This is gx, the derivative of x. You can see at it becomes 0 at x is equal to 0. Okay, so yeah. Now let's assume we choose a point very close to the origin and apply Newton's method. So let's say this is x naught, then here somewhere we'll get x1, here somewhere we'll get x2, here somewhere we'll get x3, and it will converge to this point. It will converge, uh, but there is one more trivia that I want you to know, that if you do not select this initial conditions properly, let's assume you there is a threshold. If you select it beyond this point, as beyond some certain point, I'm not telling you that point right now, but you can find that point. So and if you select it beyond, so what will happen? It will diverge. So it won't converge. So this is the problem of Newton's method, that even though it's very fast, it's very sensitive to initial condition. So sensitive to initial conditions, and it converges only if sufficiently close to So there's no guarantee of convergence. So these are some disadvantages. Even though it's faster than bisection method, these are some disadvantages. So and turns out this is a major disadvantage, and people have found various other methods which are variations of these Newton methods. Uh, that variations of these Newton method that guarantee some convergence under some conditions. Uh, and we get some similar rate of convergence as Newton's method. So it's fast also, and it guarantees some convergence. So we'll not look at those variations of Newton's method in single variable optimization. We'll look at them at multivariable optimization later in the course. So yeah, so this concludes the single variable optimization. Now let us start with the lecture that I promised you initially, the convex sets. So so convex sets, I already gave you the motivation that convex function is a very important class of functions to study optimization theory. They have some very good properties which help us simplify. Like they have single stationary points. So they have unique stationary points, and it's easy to find optimal value. So it is very easy to test convergence, prove convergence of some algorithms, or test some new algorithm on convex functions. So convex function is very important, and before studying convex functions, we should know what are convex sets. So let's start with the lecture. So before starting, let's define few definitions: lines and line segments.
Hi, Aman. I have a question.
Yeah,
Like, in the Newton method, if
yeah,
the function is not converging,
yeah,
so when you write the code, you hello,
yeah, yeah,
am I audible?
yes,
Yeah. So let's say in the Newton method, if the function is not converging, let's say because my initial condition is very far from the optimal condition, right?
yeah, yeah.
So what is the condition in which function knows that okay, I'm not able to converge?
So it doesn't know. The thing is, so if I may go up, so the thing is, if you we saw earlier that we approximate the function into quadratic function, right? So basically,
Yeah.
if the function is quadratic, so let's say we are optimizing a quadratic function, okay, and we use Newton's method, then it will always converge. So but because we are uh, approximating and some new function into quadratic, so Newton method 6, I'm still Newton method thinks that I'm still optimizing a quadratic method, but it is not actually. So that's why it doesn't know whether I will converge or not. So how do we know? It's that, so let's say you'll see that in algorithms, or in if you write an algorithm in a program, uh, your your error, so error between so let's say x naught value, this will start diverging to a very high value. So let's say your uh, 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 what should I say, your uh, our stopping value in the algorithm was derivative, right? So derivative should become lesser than some tolerance here.
Yeah.
This will never occur. That's what will happen.
Sure, sure. But then there should be some condition which should tell us that we
Yeah,
should
yeah. So
stop
right now
something.
here in algorithm we don't have. We can add that. So let's say we can add a max iteration step. So let's say is equal to any number. Let's say 1,000. So let's say if I you can add that if and max and k less than max iteration.
Sure, sure. Got it.
Yeah. So if this, like, you limit the iteration number of iteration steps. So, so that's one way of doing it. But you'll see. So actually, we don't use Newton methods that often for optimizing. You'll see if in future when we are discussing multivariable optimization, we'll use variations of these Newton method, which guarantee you convergence. So.
Sure, sure.
So yeah, let's start with convex sets. So yeah, so you already know what um, lines and line segments are. I'll quickly just let these 2 points be these two be some points x2. Let x1 and x2 be some points in Rn. So there is some n dimensional space. There are 2 points in n dimensional space, and x1 is not equal to x2. Then we can associate some parameter lambda equal to 1 at x1 and lambda equal to 0 at x2, some parameter which increases if we go beyond this point. So here it will become a lambda equal to -2. So it decreases as we go in this direction and increases as we go in this direction. Such a lambda is equal to 2, let's say. So one single parameter is associated with with some curve. Then that curve is called and you can know the which point I'm talking about just by this parameter. Then that is a line. So I'll just write it down. So line passing through x and y, x1 and x2 is, so it's a curve given by y such that y belongs to Rn, such that uh, y equals to lambda x1 plus 1 minus lambda x2, where lambda belongs to R. So you take any value of lambda, any scalar value of lambda, this point will always be on this line. So this is the basically the equation of a line in n-dimensional space. So we have seen equations of line in 2 and 3-dimensional space. This is in n-dimensional space. Remember, this is a n cross 1 vector, x1 and x2. These are points in n cross, and this is also n cross 1 vector. So this is the definition of a line. What is a line segment? I think now it's easy to look. So it is sometimes denoted by this. So ls closed x1 x2. Closed means x1 and x2 also belong to the line segment. So mm, it is a set of uh, points y belonging to Rn such that y is equal to lambda dot x1, same 1 minus lambda dot x2, but this time lambda belongs to 0 and 1. So if lambda is limited to 0 and 1, our curve will be just this line x1 x2. So this is a line segment. So this is some definition of line and line segments, and in terms of mathematically writing them down. So before learning convex sets, we should know what are affine sets. So what are affine sets? So this is so I'll just write the definition and then I'll explain. A set X as a subset of Rn is affine if for any x1 comma x2 belongs to x and lambda belongs to lambda x1 plus 1 minus lambda x1 belongs to x. So what does this definition say? So let's say we have a set X subset which is a subset of that n-dimensional space, and we have any 2 points in that space. So so any line passing, so this is the curve of a line, right? And lambda also belongs to R. It is not restricted to 0 and 1. So what does this say is, like, let's say we have a space and we have two points x1 x2, and there is a line passing through that point. So the space which the set which contains that line is called an affine set. So it should contain all the points on the line joining those 2 points. So affine set. It turns out that if you look closely, if I have any 2 points in R square, so this is a line passing, right? So this is an affine set in R square. So let's say we are talking about two-dimensional plane. We have 2 points and a line joining through this uh, is, so this is the smallest affine set that contains these 2 points. Now let's say I have a third point. So a set of these three lines can be a affine set, but that is not true because the definition says for any 2 points in that set, the line passing through those 2 points should be in the set. So any 2 points can be these also. So it turns out if there are 3 points on a three non-collinear points on a two-dimensional plane, then the smallest affine set that contains these 3 points is the whole R2 plane. So I hope you got some visual picture of what affine sets are. So um, so affine set is a set in which if you take any 2 points in the set and draw a line, that set should contain that line also. So basically that is what an affine set is. We can also extend this definition. So if X is a subset of Rn, is an affine set, and x1, x2, xk belonging to X are some k points in X, and there is a set of real numbers lambda whose sum is 1, then the point belongs to X. So basically linear combination of those points where each parameter, the sum of each parameter of those line is 1, also belongs to X, then that set is a affine set. So this is a general definition of affine set, but to visually think, you should follow so actually these two definitions are equivalent. So you should think of it like if so in any n-dimensional space, if I have 2 points, then the line joining those 2 points, if that is in the set, then it's an affine set. So let's say I take n points. So if n points, with n points, this definition is followed. And in those set of endpoints, you can also think if we take two pair of points and make a line joining them, if that all those lines are inside a set, then that is a set. Also, now all those lines that you have made, any pair of 2 points, if you take on those lines and make a line through that, all those lines should be on the in your set, then that set is an affine set. So I think that should be clear. You can ask me if you have questions. So actually I gave the example of line also. So we had discussed previously in the lecture something called subspaces. So subspaces, like this is a subspace, a line passing through, let's talk about R2 plane. A line passing through origin is a subspace. A line not passing through origin is not a subspace, but it is an affine space. And actually this is an affine set also, because if you take any 2 points, the line joining those 2 points is also in the set. This is also a affine set, but this is also a subspace. This is not a subspace. Okay, so yeah, so these are some examples of the affine sets. Um, Now there is a result which I'll state without proving. The result says that if X is an affine set and X naught belongs to X, then X minus X naught is a, these are small X naught, okay, I just, and this is a capital X, so I sum them. So X minus X naught belongs to uh, okay, so this is what is, let's say X is an affine set, and X naught is some point in that affine set. Then all the, and then the curve which is defined by this. So basically you subtract, so you basically shift that space to the origin such that X naught is at the origin. Then that forms a subspace. Okay, so that is the thing. So basically, if you look at the previous example, let's say this is X naught. If I move this affine space such that X naught goes to origin, then it becomes a subspace. So this is, I told you visually, but there is a proof associated with this. I'll not tell you the proof. I'll just tell you some structure of the proof. How will you prove it? So basically, what is a subspace? So if Y is a subspace, then any 2 points y1 and y2 belonging to Y and alpha comma beta belonging to R. So basically, and if I have 2 points in the space Y, any linear combination of those 2 points is should also be in Y. So alpha dot y1 plus beta dot uh, y2 should also be in Y. So this is what a subspace means. So how can you proceed is like you assume that X and Y1 are in Y, uh, uh, and assume Y equal to X minus X naught such that X belongs to X. You assume this, assume 2 points, then uh, then you based on those 2 points try to find the corresponding point in X. So basically, if you assume y1 and y2, you'll get y1 plus x naught and y2 plus x naught, and now you try to find what this linear combination is, and you will find that this somehow comes to a point that you can prove it to be subspace. So basically this is the structure of the proof. You can utilize it. If you want, I can make a like video later to give a formal proof of this, but it's very easy. You just give some time, it should be okay. And I hope this result is also not very like it's easy to understand why this is true. Now let's make two more definitions to for completeness, and then we'll move on to convex sets. So first definition is affine combination. Okay, so affine combination, let X be a set of points, set of discrete points. Okay, now some Y is a fine combination of points in X if Y equals to lambda 1 x1 plus lambda 2 x2 lambda k xk such that lambda 1 plus lambda 2 lambda k equal to 1. So basically a similar definition if you have k points, uh, and then y is an affine if this is true. So then y is a affine combination. And then there is one more definition, which is affine hull. What does affine hull means? Let X be a subset of Rn, the set of all affine combinations of points in X is called affine hull. Okay. So what does that mean is affine hull of X. Let X be a is same as a set of discrete points previously. So same as now I can write like this such that uh, x1, x2, xk belong to X and sigma. So what does that mean is so affine combination meant that if you take some lambdas 1 to lambda k such that their sum is 1 and take the linear combination of points in X and get some point y, it's affine combination. And what affine hull means that all the possible y's like this. So you can take multiple values of lambdas whose sum is 1. So there are infinite possible set of lambdas 1 to lambda k such that their sum is 1 and take all the points y like this, then that is affine hull. So that's what it means. So this affine hull is important. So it's not very important in our case, but this is just to introduce you to what a hull means, because will have to understand what a convex hull means. So that's why it is we are trying to understand affine hull. So now we'll move to mm, convex sets. Let's formally define what are convex sets. So yeah, so this is very important. Just try to so a set X, uh, or let's call this, because it's convex, let's call it C. A set which is subset of Rn is convex if for any x1, any 2 points x1 and x2 belonging to the set C, and any scalar lambda. Scalar lambda means lambda belongs to R, such that uh, lambda is between 1 and 0. Okay, then if lambda 1 x1 plus 1 minus lambda x2 belongs to C, then C is a convex set. So basically it's similar to affine sets. It's similar to affine set, but instead of line, it is line segment between 2 points should be inside the convex set. So by definition, it looks very similar to affine sets, but just this change makes it a whole lot interesting sets compared to affine sets. So we'll see how. So let's say I'll try to give you some examples, visual examples of how convex set look. So convex sets examples. So so this is a convex set. Okay, so you take any 2 points inside this x1 and x2, and the line segment joining those 2 points is always inside the set. This is a convex set. Okay, actually this is also a convex set, uh, the, the one I'm about to make. Okay, uh, just think of that the boundary is the set. So again, any 2 points inside the set, the line segment joining the two set, you take any 2 points. The line segment joining those point is inside the set as well. So this is a convex set. So what are non-convex sets? So examples of non-convex sets. So let's say we have something like a donut shape. Okay. Okay. Here, if you take 2 points, the whole of the line segment is not inside the set. So this is not a convex set. Okay. I hope you can see that. So a donut shaped curve in 2D is not it's not a convex set. Uh, Again, we can also, uh, let me give you one more example. So again, this C-shaped kind of set is not convex because I can find 2 points and such that the line segment joining those 2 points is not completely inside the set. So these are some examples of non-convex sets. So so you can see that that little change, instead of line, if we use line segment in the definition, it becomes the convex sets, gives you some like some very important concepts here. So yeah, we one more example that I'll give you. So let's say this single curve is a set. Then we know that this is not a convex set because any line joining these 2 points is not completely inside the set. So this is a non-convex set. But if I um, sorry, I'll just copy it rather than making a new one. But if I do here that I take all the points inside this set and increase this till infinity, it's unbounded, let's say, then any 2 points you take, it's always inside the set. So this is a convex set. Okay. There is one more example in 2D that I want to give you. So you saw a curve. If there is a curve in a 2D plane, then it's not a convex set. But there is one curve, like a straight line. It's a straight line is a convex set. Both line and line segments are convex sets. So because you take any 2 points, line segment is also inside the inside the set. So and any other curve is not a convex set. Okay, so I hope you got the point here. Now let's identify some more corner cases examples. So empty set is a convex set. So there is no notion of line segment in an empty set. So it's a convex set. Uh, any singleton set. So let's say I have only single point in a set. Then that also a convex set. And the whole of Rn space, let's the whole space, n-dimensional space is also convex set. You take any 2 points, it's inside the line segment between those 2 points is inside the set. And there is an example to closed balls and open balls. So we discussed this. So let's say I have 2D and I have some balls like this. So it's denoted by x naught, the center, and r, the radius. So x naught and r. So any ball, closed ball, this is closed ball. So closed ball means all the points on the boundary is also included in the set. And open balls, x naught comma r. So basically all the points inside, but not on, but the boundary points are not included. So this is an open ball. The above one is a closed ball. Uh, so these both are convex sets. Also, you might have realized it by now. All the affine sets are also convex sets. So affine set says that if I have 2 points, the whole line should be in the set. Here we are restricting it to line segment. So actually affine set is a um, all the affine sets are convex sets. So basically a affine set is a superset of convex sets. And we have already discussed this, that line segment is a convex set. But you might have noticed it's not an affine set, because the line passing through this, not all the points on that line are inside the set. So a line segment is a convex set, but it's not an affine set. So these are some example. Now we'll see how can we construct new convex sets from if we have two or more other convex sets, let's say. So, so we'll write possible constructs of new convex sets using okay. Yeah, so first we'll define, let's say P is a point, P is a subset of n-dimensional space, Q is a subset of n-dimensional space, and alpha is some real scalar. Okay. Then what is a scalar multiple of sets? So alpha P is a scalar multiple of set. Scalar multiple is denoted by alpha P. Let me write it like this. Alpha P. And it is denoted by all the points such that x equals to alpha p, where p belongs to set P. So let's say P is a subset of Rn. We take each point P in that set P, multiplied by some scalar alpha, and whatever new set we get, it's called a scalar multiple of the set P, and it is denoted by alpha P. Okay. Now we have sum of two sets. Okay, so it's, let's say we have P and Q. So P plus Q is a new set denoted by is X. X is equal to P plus Q, where P belongs to set P and Q belongs to set Q. So basically, you have a set P, you have a set Q. You take all the you take 1 point from P, 1 point from Q, sum it up, you get a new point. You do this for all the points in P and Q, and whatever new set you get, it's called a sum of two sets. So using these two definition, we'll state the first theorem. So we'll state these theorems without proofs, because proofs of these theorems are easy. So we'll not go on and prove it. If you require, I can get I'll upload a separate video for deriving these theorems. But right now we'll just state them. So if let Ci be is a collection of sets, a collection of convex sets. Okay. Then their integration. So basically this means C1, C2, Ck, and integration of Ci. Integration, I'm saying intersection of all these sets is also convex set. Okay, so this if we write in C1, C2, C1 intersection C2, Ck, this is what it means. Okay, so this is a theorem one. Now there is one more theorem. There are actually two more theorems. So this is the second theorem. And so if C1 and C2 are two convex sets, then C1 plus C2 is also convex. Okay. And there is, so these are basically results, and theorem 3, this says that uh, if C is a convex set and alpha is some real number, then the scalar multiple set alpha C is also convex. So this is what it is. So if you have any two convex sets, their intersection is also convex set, their sum of is also convex set, and their scalar multiple is also convex set. So it's a very good property to have for convex sets. And now let's look at some more types of sets and see their relationship with convex sets. So our first set is hyperplane. What is a hyperplane? So let B be some real number and may be some point in n-dimensional space. Then hyperplane H is represented by, and that point should not be the origin point, is represented by X such that A transpose X is equal to the real number B. Okay, so all the set of all the points which follow this thing is a hyperplane. Is a hyperplane in Rn. Let's look at R2. Okay, what is a hyperplane in R2? Okay, so it turns out that uh, a line is a hyperplane in uh, a line is a hyperplane in R2, and A is nothing but it represents uh, uh, a vector perpendicular to that line. So similarly, in 3 dimension, a plane is a hyperplane. Okay, so basically it's a linear equation. So all the curves that satisfy a linear equation in n-dimensional space are hyperplanes. So it's a linear equation variation of n-dimensional spaces. So in 4 dimension space, we don't have anything to visualize. So we call it a hyperplane. Any n-dimensional plane is a hyperplane. Now, so we already, let's look at some points to be noted. So A denotes the normal to the hyperplane. So it's a normal vector to the hyperplane. Similarly, if the A that we have chosen, it's a unit vector, then B is the distance from origin, distance of hyperplane from origin. Okay, and we have already seen that R square, in R square a line is a hyperplane, and in R cube uh, a plane is a hyperplane. Now, one more thing that I want to say, this is H given by X such that A transpose X equal to B. Let's say we choose X naught at this point. Okay, then H is all can also be represented by X A transpose X minus X naught equal to 0. So you see any vector, any difference between X and X naught, this line is perpendicular. So all the vectors where all the points X such that if you take a negative from X naught, it is perpendicular to A, then we have a hyperplane. So and the hyperplane can also be represented like this. Now let us look at some things that we'll use in optimization in general. So let's say we have a function fx, okay, and we try to plot a contour fx is equal to fx naught. Let's say this is some point x naught, and the curve that the curve at which the function values equal to this function value at x naught is a contour plot. So at each point in this curve, the value of function fx is fx naught. So this s equals so this is a set such that fx equals fx naught. Okay, so this is a contour plot. Okay, now let's x naught be here. So the thing is, all the points inside, they are actually fx less than fx naught. So fx is less than fx naught, and they're inside. Now, if we have a point, if we have a hyperplane at this x naught, so this is the first order approximation. So if you have a hyperplane at this x naught, where this is the gradient of the function g x naught, direction of the gradient of x naught, then this hyperplane is the linear approximation that we get from Taylor series. So basically you get g transpose x naught x minus x naught equals 0. So this is the hyperplane. So this concept we'll use in multivariable optimization. So I just wanted to introduce it to you here. Now we'll define something called half spaces. So what are half spaces? So half spaces are denoted by H plus, let's say, X such that A transpose X is greater than or equal to B. This is called positive half space. And there's something called negative half space, so which is X. These are also called closed positive and closed negative half space because there's an equal to sign here. So negative half space. So these are half spaces. Visually, if you want to see, so this can be denoted by H plus. This is a positive half space, and maybe the negative half space is this. Okay, so these half spaces is one thing. Now, why am I telling you all this is I want to tell you the relationship of these hyperplanes and half spaces to convex sets. So it turns out that half spaces, hyperplanes, all are convex sets. So H is convex. So this is hyperplane, right? Hyperplane is a convex set. H plus, H minus are also convex sets. And we have known that their intersection is also a convex set. So let's say we have a line here which gives us this half space. And we have a line here which gives this half space. So you can see their intersection, this point. Their intersection is this. This is also a half space. Let's say I have a third line. Then this is also a half space. The intersection of these three convex sets is also convex sets. So intersection of these three half spaces is also a closed convex set. So this is a very important property. And now let's define what's a convex hull. We defined previously what is a affine hull. Let's define what is a convex hull. So A convex hull of a set S is the intersection of all the convex sets which contain X. S n is denoted by n is denoted by convex hull of S. So we saw previously. So what does this definition say? Let's say we have a set S, and in that space, in that n-dimensional space, there are several convex set. So intersection of all those convex set which contain S is a convex hull. Now we also saw that intersection of any number of convex set is also convex. So basically, by definition, convex hull of S is convex. Okay, so basically, the smallest convex set that contains any set S is convex hull of S. So any set, so if you have a set S and we find the smallest possible convex function which contains S completely, then it's a convex hull. So we'll look at some examples, after which I think it will be very clear what is a convex hull of a set S. Let's say this is the one set S. Okay, then the convex hull will be everything inside. So this will be the convex hull of S. Convex set that contains S, smallest convex set that contains S. Now, one more example, if you want to have one more example. So basically, we saw the C-shaped curve previously. So if you see, these are non-convex functions, but its convex hull is so again the smallest convex set that contain the set S. Let's say this is set S, then this is convex hull of set S. So this is a convex. One more example of discrete points. Let's say we have a set of these 5 points. Then what is the convex set then? Then the convex set is actually use some other color. This is the smallest convex set that contains all the 5 points. Correct. This is the smallest possible convex set that contains all these 5 points. So this is S. This is convex hull of S. Let's try some mathematical curve. So S, let's say S is x1 comma x2 such that x2 is equal to x1 square. Basically, this is a parabolic equation. So if we look at it here, okay, so this is S, then what will be the convex hull of S? So it turns out that it will be, in this case, it will be okay, and it can be represented in graphical form like this. A set containing all these points is a convex set S. We'll just write convex hull of S. So I'll stop it here. So we have discussed what are convex sets. We first discussed what are affine sets. Then we discussed what are convex sets. Wrote it some property. We saw different examples of convex set like hyperplane, half spaces, line segments, line, etc. And now using this, we'll define convex functions in the next lecture. If you have any question, let me know. Until then, thank you and goodbye.